Hi guys, welcome back. We're going to be looking at chapter 14a, starting from example 3. I'm kind of going to explain example 1 and 2 kind of inside this specific example. Here in example 3, we're looking at how we can use our exact values to help us solve for reciprocal trig functions. I've kind of jumped down to one of the more interesting ones where we also look at this in terms of my Pythagorean identity. We looked at this in chapter 13b, if we can't remember, and that is the identity that cos squared plus sine squared theta is equal to 1. So my question asks us that if cosec x is equal to 7/4, find cos x. Now just note that this is cosec, and we use our third letter along, which is s, which means this is actually an inverse sine function. So let's just rewrite it as being 1 over sine x is equal to 7/4. Now, I can flip both sides of my fraction to get sine x is equal to 4/7. And now in the examples above, we looked at solving for x here, given that this was some kind of exact value. So 1/2, √3/2, 1/√2, something along those lines, and we can solve for x the same way we looked at solving for trig functions earlier on. In this question, however, I'm being asked to find cos x, not sine x. So if I'm thinking of relationships where cos and sine are linked, one of those concepts is my Pythagorean identity, which is a good way to start kind of processing or thinking about these type of questions. If I have sine and I want to find cos, most of the time I'm going to be using this identity up here. My Pythagorean identity says sine squared x plus cos squared x is equal to 1, or cos squared x plus sine squared x equals 1. If sine is 4/7, then that is going to give 4/7 squared plus cos squared x is equal to 1. So at this point, I'm just going to do a bit of an algebra rearrange to sign for cos squared x. So I'm going to subtract 4/7 squared off each side. That's going to give cos squared x equals 1 minus 4/7 squared. If I now simplify this answer here, I get 1 minus 16/49. So I'm just going to solve for this. I want to make the denominators the same. So this is going to become 49/49 minus 16/49, which is going to equal 33/49. Now this is cos squared x, so I'm going to square root both sides, which is going to give cos x is equal to the square root of 33/49. The square root of 49 is going to equal 7. So that's going to give cos x is equal to the square root of 33/7. And I should put plus or minus here out the front. So that's my solution for my first one. Again, if I'm given cosec and I'm trying to find cos, well, if I'm trying to find cos, I want to get back to sine. So I flip my fraction, or I do my reciprocal. I use my Pythagorean identity, and then I do a bit of algebra to get down to my solution. For the second example, it's really similar. However, this time I'm given a boundary condition, and we'll kind of look at how this plays into our answer. So similar idea. My third letter here is C. So I have a reciprocal cos function, and I'm trying to find sine. So in the first example, I had a reciprocal sine function. I was trying to find cos. This time I just have the opposite, but I'm given this boundary condition. This is going to be 1 over cos x is equal to -3/2, which is going to become cos x equals -2/3. Again, using my identity, I'm going to wind up with sine squared x plus cos squared x equals 1, which becomes sine squared x plus -2/3 squared equals 1. Again, subtracting that from both sides, and I get sine squared x is equal to 1 minus 4/9. If I just square the top, square the bottom, that is going to equal, if I make this 9/9, that's going to give me 5/9. So sine x is going to equal the square root of 5/9, my little plus or minus out the front, which equals the square root of 5/3, or plus or minus the square root of 5/3. Now, if I consider my boundary condition all the way back up here, my boundary condition is between pi on 2 and pi. So if this is the case, I can think of this as being between, 90 and 180. Sine is positive in quadrant 2. This boundary condition is in quadrant 2. So because sine is positive in quadrant 2, that means I actually don't have the negative part to the solution. I just have positive root 5 on 3 as my final answer. So this is how we can solve reciprocal trig functions using our Pythagorean identity. The examples earlier on, it's the exact same process, but this time when I did this step, I wound up with an exact value and then I solved for x the same way I solved for x in chapter 13.